Alrighty, here we go. Um, let's hope the audio is good in this one. I'm on streak. All right. So let's continue on with fair schedule. Okay. CFS is based on a simple concept: model process scheduling, as if the system had an ideal, perfectly multitasking processor. In such a system, each process would receive one out of n of the processor's time, where n is the number of runnable processes. So if there's three processes, then each process would be pretty much a third. Okay? And we'd schedule them for infinitely small durations so that in any measurable period, we'd have run all n processes for the same amount of time. As an example, assume we have two processes. In the standard Unix model, we might run one process for 5 milliseconds and then another process for 5 milliseconds. While running, each process would receive 100% of the processor. In an ideal perfectly multitasking processor, we would run both processes simultaneously for 10 milliseconds, each at 50% power. While running, each process would receive 100% of the processor. Oh, okay. So as we are running each process, they get the entire system as they are active. So, okay, sure. Then if we have a multitasking CPU, or I guess multi-threaded, we would run, or multi-core, we would run both processes simultaneously for 10 milliseconds each at 50% power. Okay, this latter model is called perfect multitasking. Of course, such a model is also impractical because it's not possible on a single processor to literally run multiple processes simultaneously. Moreover, it is not efficient to run processes for infinitely small durations. So this is like in an ideal world, okay? That is, there is a switching cost to preempting one process for another. The overhead of swapping one process for another and the effects on caches, for example. Okay, so I'm guessing that when we context switch, we clear the CPU cache every single time. Can we validate that? Let's see. Does the CPU cache get cleared during process context switches? I'm wondering if the CPU cache gets cleared, which is what they're trying to say, because that's a lot of overhead. Because when you context switch a lot, then you clear your cache. That's actually quite expensive in that case. Wow, I really need to improve the speed of this thing, but let's see. And now I'll just go back to the command line version. But it's supposed to look up like, documentation and things like that. So it's probably doing something expensive regarding that. So yeah, gotta make this faster. I hope that when it comes up, it's good. Otherwise, I'll just look up the internet. I would like to see it come up though. Mm. Okay, I quit. Let's look it up on the internet. Let's see. Okay. CPU cache cleared on process context switch. C, is a processor cache flushed during context switch? Necessary cookies only. Ugh. Okay, is the processor cache flushed during context switch in multi-core? Not what I'm looking for, actually. How about this one? Okay, are L1 and L2 caches flushed on context switch on Intel processors? Okay, mostly correct. Haven't found a definitive answer here. It looks like caches are VIPT, virtually indexed and physically tagged, which means that even on a context switch, the new process may hit the cache on the basis of the virtual address, but may or may not hit it due to physical address. So correctness won't be satisfied if we don't flush the cache. Okay. Oh, for Intel chips, L1, L2, and L3 and L4 are typically PIPT and never flushed. Okay. That would be a disaster for cache coherency. Okay. So what happens to cache context on a context switch? Wow, there's so much junk here. In a multi-core processor, what happens to the contents of a core's cache, let's say L1, when a context switch occurs on that cache? Is the behavior dependent on the architecture, or is it a general behavior followed by all chip manufacturers? So that depends both on the processor. It can vary from model to model and the operating systems, but there are general principles. Whether a processor is multi-core has no direct impact on this aspect. The same process could be executed on multiple cores simultaneously if it's multi-threaded, and memory can be shared between processes. So cache synchronization is unavoidable regardless of what happens on a context switch. So I'm guessing no, cache is not flushed or cleared. When a processor looks up a memory location in the cache, if there is an MMU, it can either use the physical or the virtual address of that location. Sure. Okay, with physical addresses, it doesn't matter which processor is accessing the address. The contents can be shared, so there's no need to invalidate the cache during a context switch. Done. Found the answer. Good. I'm happy. So no cache invalidation on a context switch. I don't think that thing is gonna finish. All right. So for example, thus, although we'd like to run processes for very small durations, CFS is mindful of the overhead and performance hit in doing so. Instead, CFS, complete fair scheduler, will run each process for the same amount of time, round robin, selecting next the process that has run the least. Okay, so CFS will run each process for some amount of time in a round robin fashion. Okay, selecting the next process that has run the least. So it'll select the next process that gets chosen in CFS scheduling is going to be the process that has run the least time so far. Got it. Okay. Sure. Okay. Rather than assign each process a time slice, CFS calculates how long a process should run as a function of the total number of runnable processes, rather than assign each process a time slice. So no time slice. Processes don't get time slices. CFS calculates how long a process should run as a function of a total number of runnable processes. Okay, so there's no fixed time slice, but it's a dynamically calculated value based, I guess, it's dependent, runs as a function of the total number of runnable processes. So the more processes you have, I think that's going to affect how things are going to be scheduled. Instead of using the nice value to calculate a time slice, CFS uses the nice value to weight the proportion of processor a process is to receive. Higher valued, lower priority processes receive a fractional weight relative to the default nice value, whereas lower value, higher priority processes receive a larger weight. Okay, let me try to make sense of that. So they're saying that if you have a higher nice value, then you're going to get more processor. Okay, you still kind of run, I guess you run for more time. In this case, if you're a higher priority, meaning lower nice value. Okay, each processor then runs for a time slice. This is like the dynamically calculated one, proportional to its weight divided by the total weight of all runnable threads. To calculate the actual time slice, CFS sets a target for its approximation of the infinitely small scheduling duration in perfect multitasking. This target is called the targeted latency. Smaller targets yield better interactivity and a closer approximation to perfect multitasking, at the expense of higher switching costs and thus worse overall throughput. Smaller targets yield better interactivity, okay, because you're getting queued up to run more often, and a closer approximation to perfect multitasking at the expense of higher switching costs because you're switching more often for other processes and thus worse overall throughput. So since you're switching so much, you're not really getting that much work done, spending all your time just context switching. So let's assume that the targeted latency is 20 milliseconds. Okay. So to calculate the actual time, the CFS sets a target for its approximation of the infinitely small scheduling duration in multitasking. This target is called targeted latency. Okay, so that's 20 milliseconds, and we have two runnable tasks at the same priority. Regardless of those tasks' priority, each will run for 10 milliseconds before preempting in favor of the other. So equal. Okay. So we have four tasks at the same priority. Each will run for 5 milliseconds. Okay, makes sense so far. And we have to remember that they're at the same priority. If there are 20 tasks, each will run for 1 millisecond. Okay. So because the targeted latency is 20 milliseconds, so everything I think what they're saying that is targeted latency is the amount of time where all runnable processes have to run. I guess at least for that round. Okay. Now we all have the same priority, then all of them are going to run for 1 millisecond in this case. Sure. So note, as the number of runnable tasks approaches infinity, the proportion of allotted processor and assigned time slice approaches zero. Okay, that's true because the more processes we get, the more context switching we have to do because there's less time. So really, the runnable time is just getting so small that it's zero. As this will eventually result in unacceptable switching costs, CFS imposes a floor on the time slice assigned to each process. This floor is called the minimum granularity. By default, it is 1 millisecond. So that's the smallest it can go for what we call it, targeted latency, right? If you're a process that's running within that targeted latency, the smallest amount of time you can get is 1 millisecond. That's it. That's like the worst you can do in this case. Thus, even as the number of runnable processes approaches infinity, each will run for at least 1 millisecond to ensure there is a ceiling on the incurred switching cost. Astute readers will note that CFS is thus not perfectly fair when the number of processes grows so large that the calculated proportion is floored by the minimum granularity. This is true, although modifications to fair queuing exist to improve upon this fairness. CFS was explicitly designed to make this trade-off. In the common case of only a handful of runnable processes, CFS is perfectly fair. Okay, so let's actually try to parse all that just now. So we have something called a targeted latency. And let's just say for this example, we're going to do 10 milliseconds. And let's say we have processes. We have task 1, task 2, in this stage, right? So that means in the queue, let's say task 2 runs first and then task 1. If we're going by completely fair scheduler, in order to process this entire queue, T2 has to run for 5 milliseconds, and then T1 has to run for 5 milliseconds, and then again, maybe T1 gets 5 milliseconds, and then T2 gets 5 milliseconds. round robin. I don't know. So here is that targeted latency. Everything must run. Okay. Okay. So now let's introduce a third process in this case. So same targeted latency. Okay. But now we have three processes. How would that look like? This is just my interpretation of what we just read. Okay. So in this case, let's just run T2 for, in this case, 3.33 milliseconds. And then we'll run T1 for 3.33 milliseconds. And then we'll run T3 for 3.33 milliseconds. And right here now is that targeted latency. Okay? So that's one round of running. And then again, T2, T1, and finally T3 for 3.33, 3.33, 3.33, and that reaches the target latency. And then we do the same thing onwards, right? Now suppose what I just read, its target latency again is 10 milliseconds. Okay, but now we have 100, or sorry, we have T1 all the way to T100. Okay, like that. Make sure that's a 0. Okay, so what that means is that we're going to run this for 1 milliseconds for T1. T2 is another 1 milliseconds. And then we'll just keep doing 1 millisecond until we hit T100. I don't know what this means here because now we're at 100 milliseconds. So what does that actually mean? So it broke the targeted latency. So it has, I'm not sure what it does here when it's 10 milliseconds because the granularity here is 1 millisecond, right? That's the minimum. Minimum time is 1 millisecond in this case. Okay, so if we had 100, they're saying that it's not completely fair in this case when that happens, and that's like the flaw. Okay, so here, each process will run for at least 1 millisecond to ensure that there's a ceiling on the incurred switching cost because we don't want to go lower, otherwise context switching is going to be very expensive. Okay. Okay. So I'm guessing that. Okay. So I'm guessing that it does something. It probably just moves on and it misses the target, but it just continues doing what it needs to do. So, okay. So now let's again consider the case of two runnable processes, except with the similar nice values. Say one with the default nice value of 0. Oh, by the way, this example I guess we were doing right here assumes that all the nice values were the same. So all the same priorities. Okay, so say one with the default nice value 0 and one with a nice value of 5. These nice values have dissimilar weights and thus our two processes receive different proportions of the processor's time. In this case, the weights work out to about a third penalty for the nice 5 process. If our targeted latency is again 20 milliseconds, our two processes will receive 15 milliseconds and 5 milliseconds each of processor time, respectively. Okay, makes sense. Because it has to run both processes within that targeted latency. So that's like the pie. The whole pie is a targeted latency. Now, depending on that priority, a specific process is going to get more running time. But this running time is always going to be different depending on the nice stuff. So, okay. Oopsie. My monitor just. Okay. All right. So now say our two runnable processes instead had nice values of 10 and 15. What would be the allotted time slices? Again, 10 and 5 milliseconds each. Absolute nice values no longer affect scheduling decisions. Only relative values affect the proportion of processor time allotted. So we go from, what was it, 0 and 5, 10 and 15? Same thing. Okay? Um, How do they calculate? Okay, fine. We assume that the weights work out to about 1/3 penalty for the nice 5 process. Okay. So yeah, again, 15 and 5 milliseconds each. Absolute nice values have no longer affecting scheduling decisions. Only relative values affect the proportion of the processor's time allotted. So put generally, the proportion of processor time that any process receives is determined only by the relative difference in niceness between it and other runnable processes. The nice values, instead of yielding additive increases to time slices, yield geometric differences. The absolute time slice allotted to any nice value is not an absolute number, but a given proportion of the processor. So proportion. Okay, proportion based off of the targeted latency, I'm assuming. So CFS is called a fair scheduler because it gives each process a fair share or proportion of the processor's time. As mentioned, note that CFS isn't perfectly fair because it only approximates perfect multitasking, but it can place a lower bound on latency n for n runnable processes on the unfairness. So the lower bound is going to be that 1 millisecond. Okay, time for potentially some code. Let's see. So the Linux scheduling implementation. With the discussion of the motivation for and logic of CFS behind us, we can now explore CFS's actual implementation, which lives in kernel/schedfair.c. Okay, I'm so excited. I'm just going to go there right now. Okay, this is never going to go. Okay, you know what? I'm just going to open up another one with my terminal version. Okay, let's do that. Llama run llama 3.1 AP. Let's do that. Okay, then we can ask it. It might be smart. Who knows? Okay, so let's do search for file. Let's do sketchfair.c. It's a network drive, so let's hope. Okay, kernel sketchfair.c. Okay, so copyrighted 2007 by Red Hat. Igno Molnar. Good job. Ingo. Good job, Ingo. Okay. So this is the implementation. Okay, great. So actually let's read some comments. Okay, let's read some comments. Okay. Completely fair scheduling class. So a lot of people have actually contributed to this. And for the time, let's pretend we're in 2010. This is like the last change was 2007 most likely. So targeted preemption latency for CPU bound task. Default is 5 milliseconds times 1 plus ilog number of CPUs. So it's based off of number of CPUs, I guess. Units and nanoseconds. This latency value is not the same as the concept of the time slice length. Time slices in CFS are of variable length and have no persistent notion like in traditional time slice based scheduling concepts. So yes, see already the code is telling us that the scheduler does not make use of a fixed time slice. Okay, to see the precise effective time slice length of your workload, run VM stat and monitor constant switches. Okay, that's good to know. Okay, so this is 5 milliseconds, I guess. Okay, in terms of the nanoseconds, so it's like 1, 2, 3, 1, 2, 3. Yeah. Okay, so this is tunable. Okay, let's just go back to the book and see what we find. Okay. So specifically, we discussed 4 components of CFS. Time accounting, okay, that's great to know. Process selection, so how the processes are chosen. And then schedule entry point. Ooh, this is gonna be fun. And then sleeping and waking up. So when they say sleeping and waking up, I don't think they mean by the computer, they mean by the process. Okay, so time accounting. All process schedulers must account for the time that a process runs. Most Unix systems do so, as discussed earlier, by assigning each process a time slice. On each tick of the system clock, the time slice is decremented by the tick period. Okay? When the time slice reaches 0, the process is preempted in favor of another runnable process with a non-zero time slice. That's interesting. There's like an opportunity for logging right there. So, okay. So there's a tick. Okay. The scheduler entity structure. CFS does not have the notion of a time slice, but it still must keep account for the time that each process runs, because it needs to ensure that each process runs only for its fair share of the processor. CFS uses a scheduler entity structure, struct, schedule entity, defined in Schedule H to keep track of process accounting. Okay, so I would assume that this stuff is going to be the time, because it's a unsigned 64-bit int. Okay, I'm guessing this is some boolean on the run queue, most likely. Telling it might be on run queue. Okay, interesting. And then many stat variables, literally only if whatever set. I don't know what that means. Okay, the scheduler entity structure is embedded in the process descriptor stuck in the struct task struct as a member variable SE. We discussed the process descriptor in whatever process management. Okay, so if we were to go here, there's a scheduler entity, schedule entity. Okay, static inline task struct task of. Is there something that defines it? Okay. Oh, 95 of these. Let's where is it? Define a schedule H. So we're not even in the right file. So let's do schedule.h. Okay. And then let's do schedule entity. Okay, so right here. So it's pretty much exactly like what the book said. Load for load balancing. That's interesting. Ooh, interesting. CFS stats for schedule entity. Current field usage histogram. Okay, interesting. So cool. Pretty much these are only if sketch stats configuration is enabled in the kernel, and fair group scheduler. I'm guessing. Okay, cool. Now, where was task struct again? Um, where is task struct defined in the Linux kernel 2.6 source code? I want to say it was task thread schedule. What? Schedule.h. Okay. Around, no, it's not around line 100. I keep forgetting. So I'm already on schedule.h. So task struct. Oh, yeah, it was schedule.h. Not definitely not line 100. Okay. So if we were to go here and look for our sketch entity, we would see an SE somewhere here. Uh, huh. So should we just type it and trust it? So SE like this? No. Sketch entity SE. There we go. Yeah, where okay, so this is defined in here. Okay, great. So we do have every task does have a scheduler entity. That's good. Okay, go back here. Let's go back to the top. Okay, so fair. So the virtual runtime, the v runtime variable stores the virtual runtime of the process, which is the actual runtime, the amount of time spent running, normalized or weighted by the number of runnable processes. Wait, v runtime, is that somewhere here? Ah, right here. So this is the time. Okay, so virtual runtime of the process, which is the actual runtime, normalized by the number of runnable processes. The virtual runtime's units are nanoseconds, and therefore v-runtime is decoupled from the timer tick. So different from the timer tick. It's just like in real world time units. The virtual runtime is used to help us approximate the ideal multitasking processor that CFS is modeling. With such an ideal processor, we wouldn't need v-runtime, okay? Because all runnable processes would be perfectly multitasked. That is, on an ideal processor, the virtual runtime of all processes of the same priority would be identical. All tasks would have received an equal fair share of the processor. Because processors are not capable of perfect multitasking and we must run each process in succession. CFS uses v-runtime to account for how long a process has run and thus how much longer it has ought to run. Okay, so if it's like super fair, every process gets the same amount of time to run, v-runtime will be used to compare those times. So the function update cur defined in sketchfair.c manages accounting. Ooh, interesting. So struct sketch entity, the cur. So this is the current sketch entity. Completely fair schedule run queue, I'm assuming. Current running process. Or the current schedule entity. Now, so the clock. What is this? The run queue of CFS. Okay, sure. I'm guessing run queue takes a dynamic run queue of some other scheduler. So get that current clock. Okay, and remember, unlikely means like there's an optimization saying that most likely this is not going to happen often. So yeah, anyway, get the amount of time the current task is running since the last time we changed the load. Okay, so now versus when we started, this cannot overflow on 32 bits. Delta exec. Why is the start being used? Let's see. Update cur with this new value. Okay. Oh, because that's exec start gets updated to the next one. I'm guessing that's probably to prevent like some sort of weird loop. Uh, oh no! This was supposed to model the perfect multitasking processor. So we're only interested in the amount of time it has run so far from the last round it had been scheduled. I'm guessing. Okay. Okay. So entity is task. Okay. Let's say it is task of. So it's getting the task struct by using task of this scheduler entity. Okay. Looks like it does some tracing, CPU, ACCT charge, counting deduction. I don't know. Group exec runtime. Okay, so this is a mystery to me, but I think let's read on. The book might say something. So update cur calculates the execution time of the current process and stores the value in delta exec. Okay, makes sense. It then passes the runtime to update cur, which update which weights the time by the number of runnable processes. Okay, the current process's v runtime is then incremented by the weighted value. Sure. So this is update cur. This This call here goes down to this function. Okay. So this takes in the completely fair schedule run queue, the pointer to it. It also takes in a pointer to the schedule entity, and then the delta, the time delta it has executed since the last time it run. Okay. Then what do we do? Looks like so there's the declaration of waited time. Okay. And that eventually gets set or incremented with v runtime. Okay. Update curves invoked periodically by the system timer and also whenever a process becomes runnable or be, or blocks becoming unrunnable. In this manner, v runtime is an accurate measure of the runtime of a given process and an indicator of what process should run next. Interesting. In the last section for process selection, we discussed, or process selection. In the last section, we discussed how vRuntime on an ideal perfectly multitasking processor would be identical among all runnable processes. In reality, we cannot perfectly multitask, so CFS attempts to balance a process's virtual runtime with one simple rule. When CFS is deciding what process to run next, it picks the process with the smallest vRuntime. Ooh, interesting. This is in fact the core of CFS scheduling algorithm. Pick the task with the smallest vRuntime. That's it. Okay. So the how the CFS scheduler will choose the next process to run is just the one with the smallest v runtime. That's interesting. I think we could exploit something to just make a change just for fun. Okay, so the rest of this subsection describes how the selection of the process with the smallest v runtime is implemented. Interesting. Okay, so CFS uses a red-black tree to manage the list of runnable processes and efficiently find the process with the smallest v runtime. So what is a red-black tree? Okay. Okay, a red-black tree called an RB tree in Linux is a type of self-balancing binary search tree. Okay, we discussed self-balancing binary search trees in general and red-black trees in particular in chapter 6. Okay, so let's not worry about it for now. For now, if you're unfamiliar, you need to know only that red-black trees are a data structure that stores nodes of arbitrary data. So the nodes contain the data identified by a specific key, and that they enable efficient search for a given key. So because it's basically a binary search tree search, and it's self-balancing. So then the searches tend to be really fast. You don't really go that deep because the tree is always being balanced. Versus a balanced search tree that isn't self-balancing, it could become very linear, or it could degenerate into like a very linear tree. So specifically, obtaining a node identified by a given key is logarithmic in time as a function of total nodes in the tree. Okay, so let's see how it picks the next task. Let's start with the assumption that we have a red-black tree populated with every runnable process in the system, where the key for each node is the runnable process's virtual runtime. Okay, so the key is the v runtime, the total time it has run for that moment, or like that last round or something like that. Okay. So given this tree, the process that CFS wants to run next, which is the process with the smallest v runtime, is the leftmost node in the tree. Oh, I see. That's how it's being implemented. Okay, so let's forget about it being red black. Okay, so pretend this is a CFS queue, and it's just a regular BST, not red black first. So basically, when we add a node here, let's just say this is task 1, okay, and it's v runtime. Let's just call it VRT. V runtime is going to be, let's say, at this point 100 or something. Okay, so then when we take out task 2 and put it back in, it's going to have a specific runtime so far. Okay, that has a v runtime of maybe 67. Maybe there's another task that is task 3 that has a v runtime of maybe 124. Okay, so at some point, let's say that we dequeue task 2 and then queue it back up. At some point, then maybe it ends up like this: v runtime 100. Okay, and since we had to update things, now we have task 3, which is v runtime 124. Let's say task 2 ran for a very long time, and now it is 105 or something. I think that's what they're trying to do, like that. So that's like the delta. It ran for an extra 105, and now it's 105. So now the leftmost will still be task 2. No, the leftmost in this case is null, right? So then task 1 eventually gets picked next. Okay, so task 1 gets picked next, and now we end up in this state. Most likely it could be, right, where we have task 2 is like the runtime 105, and then task 3 is still 104. Let's just do it like this now, and maybe 124, sorry, and then now maybe task 1 is like 150. And it could be like on the next round, task 3. It could be we could get to a state where task 3 had only run for maybe 3, right? And then now we're back at the state here. So 105. Then we'll have task 1 at 150. I think this is what they're trying to say. So that tree is always like shifting based off of that v runtime. That's like the time that it has run at certain points. Okay. That is, if you follow the tree from root down through the left child and continue moving left until you reach a leaf node, you'll find that the process with the smallest v runtime. Again, if you're unfamiliar with binary search trees, don't worry. Just know that this process is efficient. Hey, I actually think this is clever. CFS's process selection algorithm is thus summed up as: run the process represented by the leftmost node in the red-black tree. Okay, in this case, what we assumed was a regular binary search tree. Okay, so the function that performs the selection is called pick next entity, defined in kernel sketchfair.c. Okay, so let's look at this little code snippet there. Okay, so I'm going to do something crazy. Let's do this. Pick next entity. So we have this here. Why don't we do print k kern info? Is it kern info? Is it kern info? Are the options for print k? They start with kern. Can you tell me? So what are the options for print k? They start with kern. Can you tell me? Oh yeah, Olama kind of unloads the model after a while. I need to set it so that it doesn't do that. I think it's just kernel info, and then I'm gonna say the process to be picked next is, okay. In this case, kern emerge. Okay, so yeah, we did do current info. That's correct. I remember now. So the process to be picked next is, let's just do the name, okay, with v runtime %d, and then that will be, okay, so this is going to be average dev as a tag. And what will we put here for, so because we have the node, but I don't know what this is. This results in something. How do we get the task of? Is it just task of? Can we actually get, okay, what function can we call to get the task struct of an RB node in the CFS scheduler for the Linux 2.6 kernel. So what function can we call? To retrieve the task associated under you follow function RB task. Okay. This function has been deprecated. A better approach would be following RB entry task. This is in sketchfair.c and takes an RB root, the root of the tree, and an RB node. Okay, so here's how we can use it. So we want to get the task because this is actually the sketch entity. I want to get the task struct itself and print out the name, and then I want to also print out this the task structs not task struct, the sketch entities v runtime. So basically what I'm thinking about is something like this. In this case, pretend my or we say cur task com, and then we can say left is it v runtime, something like this is what I'm looking for. So left is this one right here, the sketch entity, which should be non-null at this point, and then we want to get the current task. So do we even have include on? Okay, so we don't have an include on fair.c. So what would we do here? Do we include fair.h? Include the file fair.h in kernel sketch fair.h. Use the macros related to complete fair scheduler. So code things like this. Really? Kernel sketch fair.h for the RB entry task. Really? Okay, so part of the kernel source and provides the necessary definition of working with the CFS. Okay, sure. Wait, but I'm wondering, like, we get the root. What is P? What is P? P is a current node. Okay. Oh, P is the pointer to the task struct. No, that's not what I want. RB entry task root node. Oh, this is the other way around. This is getting the RB node associated with the task. I want the other way around. Okay. How do we retrieve the associated task struct given a sketch entity struct? Let's do it this way. Say task struct and sketch entity. You can use the following function. Task struct entity task. This is declared in fair.c. Okay. Same thing, right? But to get task struct from a sketch entity, you can also use the following function. Sketch entity PSE. Oh, okay. So assuming that we have a sketch entity, we could do SE task. SE task. And the corresponding RB node. You need access to the root. Forget it. You know what? Let's just do. Okay, let's just do this. I know that you can do some like pointer crazy math to do this, but entity task. Why does it say? Why does this say that it's deprecated? Okay, that's fine. You know what? Let's just do this for now, and then let's figure it out. Let's get some confidence. So we made our next kernel change. And again, since we saved it, we can go here. I need to refresh this. This is probably outdated. Okay, so we can go here. This should have our changes. Okay, so we have everything mounted most likely. If we were to, let's say, again, go to kernel sketch fair. So vim kernel sketch fair.c. Then we search for average dev. Right, so it's right there. Okay, so then we can just do I think we just do make. I'm gonna do something crazy. I'm gonna do say make I increased the number of cores on this thing. I did 24. Okay, so I've done 24. So I'm gonna do make J 48. And you know what? I'm gonna be brave and do 96. See how fast it goes. It's also compiling on top of whatever we had, I think. So it should be faster. Oh, make error 2 struct RB node has no member B runtime. Oh, why not? Oh, because that's a rep. Oh, it's an RB node. Okay, so that's not the sketch entity. Oh, it's starting to make sense now. Okay. Okay. So this is of course. Okay. So left is RB entry is right here. So that's the red black entry. That gives us back. I gotta think harder now. Okay. So RB entry is defined where? Oh, I think where is RB entry? Okay. Where is RB entry defined? Because left was just the RB node. We want to get the RB entry of the sketch entity. So, oh, it's defined in that generic data structure. So we have to kind of get it. Okay, so we can just assign this a variable. We can trust that this is a sketch entity because it does return the sketch entity here. So then we can just do something like this: struct sketch entity result, and that's going to be RB entry left struct sketch entity, which is the type here, and then the run node. I have no clue what that means. What is a run node? Okay, whatever. Run node. Okay, so then we have result, and then we can say, well, this is now result, and then we can just get rid of that and say return result, and that should give us what we want. Yeah, so we get the result here, and this should be the sketch entity now, and then we can get the v runtime and then return that result. Let's be brave again to do this. Let's see what happens. Okay. I really hope this compiles quick. I have so many CPUs, but the problem is that Lizzie types in. U64. Okay, I'm gonna do the right thing. I think it's long LLT. My C is getting rusty again. Didn't code for a while. I think it's LLT. Okay. Forbids mixed declarations and code. That's okay. This is in C90. Warning. That's still fine, right? Should be C99 by now. Should still be fine. I'm guessing. Okay. So let's see what kind of numbers we get for v runtime. I'm wondering. It would be also awesome if we can also figure out like, oh, what round is this and what process. But let's do one thing at a time and just do some exploration. Oh, this is so slow, but it looks like it's okay. Okay. I think it's trying to like find a difference. Okay, that looks good. Oh my god. Hey, come on. I'm still not used to how slow this thing compiles. It seems much faster when you like go from clean, but that's just me tricking myself. I think it's genuinely trying to just find differences. Okay, so it's done. This is an incremental build. I'm assuming that's okay. So I just do sudo make install. And I do sudo update grub for the new kernel. If it's not incremental, if incremental doesn't work that way, we learned, right? So let's see what we reboot. Let's see what happens. So yeah, I'm actually curious, like what these v runtime numbers actually look like, just for the sake of education. So let's start that. Let's see if we crashed our kernel. Oh, look at that. These are big numbers. But that's because they're in nanoseconds. Nice. Okay. It's happening so fast that that's a lot of logging. So V runtimes are that big. Let's see. 1, 2, 3, 4. Oh, I can't. No, forget it. I'll just look at the log later. But these are ridiculously big numbers because they're in nanoseconds. I'm not sure if it's like worth even like sitting because I think the logging is probably gonna slow everything down. So let's proceed. Okay, so we know we can get all these numbers now, and now I would like to actually get the task, the task struct associated is. So it should be a little easier now. So how do we retrieve the task struct from a sketch entity? I should have said from Linux kernel. Oh, but okay. I don't even know if it's ever gonna finish now because the logging is just slowing it down like crazy. We'll see. All right. Oh, I wonder what the CPU is like too. So we do have a lot of CPU activity, 4%. So that means one core must be working really hard doing this. Okay. All right. So I'm guessing that we can use something like task of or task of sketch entity or something like that. In fact, let's see if we can do something like that. So task of, I saw something was like task of, but I'm not sure if RT task of, is there like a, oh, task of SE. Ooh, that's interesting. Task of SE. What is this? Task struct. Pick next task type. So this is a scheduler entity, which is a pointer, and the task of. Let's do that. Let's go. Okay, so we can do struct task struct t sk task of result. Okay, and then maybe we could say the process to be picked is going to be this with the runtime that, and then tsk com. Why not? This is gonna take forever. uh, should we do it again? Yeah, let's do it. Okay, let's boot into our other kernel. And you know what? This is taking too long, so but you know what? Let's just do it. Let's just explore like what exactly these processes are, even though like it's still doing its boot up thing. But of course, there are processes being scheduled, and I do see progress is being made because sometimes you see extra logging somewhere. So yeah, I'd say why not? Let's just recompile the kernel again. So if I were to so here's what happens. Like if you get to a bad state like this, right? Like let's just say you get to a bad state. What I tend to do is I just shut down like this, boom, kill it, and I'm gonna go back to the original kernel that I had because it still works, right? It doesn't. It's not using the one that we screwed around with. So instead of picking the first one, let's go back to 2.632, and that's a good one. That's like from canonical in this case. Ooh, did I mess things up that bad? Or maybe it just needs a refresh. Oh, I probably broke my system. Oh no. It's supposed to do something. It's supposed to do something. Oh no. Oh, it just took a while. Okay. Okay, so I'm just gonna compile again and just see what at least the names appear. So I'm assuming this is how we get the task. We do task of. So and I'm guessing we need to refresh again. There we go. Oh boy. Okay. So that's how you recover it back to your original kernel. Then we just do the same thing here again. We can just do, since we're mounted already, I trust that it works. We should say make J24. But to be honest, I don't think it makes a difference. So, in fact, maybe it's faster. Who knows? So, let's see. Oh, I do see that sketch is being updated. Yeah, it doesn't matter. It doesn't really use everything anyway. It would have been like maybe like a like way higher in terms of usage. It was leveraging all these cores. So yeah, we know for sure the warnings don't really matter as much. So yeah, so just to review, task struct is so we get the pointer to the task struct, TSK, based off of the sketch entity. I think this is a very good helper function. And then we're just gonna print out exactly what some of these processes are. Of course, logging it like this, since everything's working so quickly, there's so many of these loggings, and it's just too slow. So we just want to get to a point where we can at least see what's going on a little bit during the boot up process. So yeah, I guess incremental like compiles aren't that bad. At least I have time to do two, but I'm gonna call it after we do this quick verification and then talk next time. So. Mm, okay. Okay. Done. All right. So sudo make install. Okay. So that's gonna install the kernel. Sudo update grub. Okay, consider reboot. Moment of truth. I wonder what was that chatty process. Probably in it. Okay, let's see what happens. We went to the 2.634 kernel again. Hopefully with our changes, like our additional changes. Okay. So, okay. Oh, K swapper, K thread D. Okay, all these things. So that's what's doing it. So no idea yet. So yeah, that's it. At least we can put stuff like that out. Not a good idea. Not a good idea. But we did something. So and by the way, yeah. So these V runtimes are huge, but that's because I think they're nanoseconds. Anyway, talk to you soon.